A couple, yeah, I guess. I think they might have changed things around on Canvas. Um, I tried to upload some files as we had used for uploading PDF to the quizzes and stuff in 303. We couldn't see the same buttons today. But anyway, in files on our homepage in Canvas, I reminded myself today, I guess I must be getting senile, that in the files on Canvas are the 3 books for this course. And so you don't necessarily have to go hunting around to find them. So I see that we have Glass's book, Grant and Bixley, and also the Rosen and Cooey, there's a second double-barreled name. I don't remember the second part of it, the heat pump book. So those are all available to you as PDFs. So that's something you can get. The other thing I added was to add presentations and lectures. And today there's a PowerPoint, actually a PDF file of the PowerPoint that we used today. So if you want, it's quite a big file because it's, I think it's lots of slides. So what I do to make PowerPoints is sometimes I end up with a big file and I just put a bunch of the slides so you can't see them, or the audience can't see them. And so I think it is a big file. No, it says it's 41. I thought it was more than 41 slides actually. Anyway. So anyways, you can access that if you so wish, and we'll use that later. I'm not a great believer in PowerPoint, as you know. I just don't think it's a very good, much more, prefer to be a bit more interactive and use Notability. And so now I can't see exactly, because of half my screen being blocked, that to make it, oh, I didn't want to do that. So I guess I could show it from Canvas. Anyway, so you can actually access that file if you want to get it. And I'll endeavor to put on Canvas the materials that we talk about each day. It won't be much more than the same kind of, I don't have a ready-made set of files for this class, as I mentioned on Tuesday, but I will endeavor to upload. I'm still letting people come in. So I guess, yeah, so as people come in, it's 7 minutes after. I just don't want to keep on hitting the button to get people in. So please try and join us early, even though it's not perhaps so critical right now. So I'll try and share with you whatever I have on Notability as a PDF file. I don't know why it won't go a full screen today. That seems strange. These were web links. The nuclear power one is what we just looked at. I didn't put this online, so I'm not actually going through this. Watson AGU talk is about climate change type things. I'm not going to go through these things. I guess these were the introductory videos if people wanted them, but I guess we're at the witching hour, so I'll forge ahead. So really only 2 announcements. One is that on Canvas, those books are available, and also the material for the class in terms of the course material is available under files. I would put it somewhere a bit more accessible, but I don't know quite how to do that yet. So, because it seems like they changed the interface. So that's one thing. And the other one is the email I sent out to get you to log in on your own, on your Penn State credentials if you're using Zoom. And so the reason for that is that I can download a file of participants with their, how long they participated. Of course, it doesn't say any more than the fact that you were logged on. It doesn't say how you were participating or if, and that's fine. And I can take that stuff down from there. I did it already for the first class. For those of you who are logged on different credentials, I put a 0.5 against your grade for that instead of 1. And I'll change that if you're logged on today, etc. on your Penn State stuff. So that's the way. I did get a couple of suggestions from people in the class about holding up a QR code and taking a roll call, and I've thought about all those things, but I'm not super excited about them just because I've always thought that this should be an adult kind of thing, and that seems a bit not the suggestion being juvenile, but doing those things seems a bit juvenile, and so I don't want to do it. I could spring a question on you and get you to give me an answer, or write a chat question answer, but let's see how I can do it just by harvesting the information down from Canvas as we go through. So that's the only two announcements I think I have. Yes, I'm just looking at my notes next door. So what I want to do today, and I say as I'm not a great fan of this, but this is the way I'll do it nonetheless, is to use this presentation to really look at the big picture, I guess, of this class, or the premise, I suppose, of this class. And that is the question of why should we even consider geothermal energy as a source when we have perfectly good coal floating around, basically, which is what's powering or has powered our grid and powered the computer that we're talking on right now. Probably it might not be so much coal that's supplying the electrons to my machine right now, but it might be natural gas. But we'll talk about kind of the big picture, the drivers for this class. And this actually is a presentation that I've used many times. The last time it was given, I'm reminded, was in Thames, New Zealand, to a Rotary Club in March of 2019 by invitation. And the premise was that we were taking our Sustainable Energy in New Zealand class there, and it was after all the students, we'd taken them to the airport and they departed. And so the big question here is, the class is really looking at subsurface sources of energy, geothermal energy, but there are lots of other sources of energy and uses of the subsurface which relate to energy, which are relevant to this class. And so I'll give you some kind of background in terms of those. And of course, these are all options, as I admit someone else, Amir. These are all options in terms of the big picture. It's not just geothermal energy, but it impacts on nuclear power because nuclear waste have to be disposed of somewhere, and that's typically in the subsurface. If you want to keep on burning fossil fuels, then disposing of carbon in the subsurface is feasible, not really cost effective, but feasible. And there are different reserves of subsurface resources that can also be used in supplying the energy budget. So talk in general about energy supply, we'll talk about low carbon fuel solutions, as you see in red here. Business as usual, carbon management solutions is business as usual, burning fossil fuels, but dealing with the discharge in some way. And then zero carbon solutions, of which geothermal is one of them that we'll talk about. So that's it. Why isn't it advancing? Oh. As I said before, this is I've given this in the class and also when we traveled to New Zealand, but we run for, I guess 20 years was our first course class. 2020, we took some students to the Intermountain West. Kind of the theme was energy supply, went to NREL, National Renewable Energy Lab in Denver, and then went on to the California from there. In 2003, we added a course which we called it Industrial Revolution to Industrial Ecology, kind of taking the course from the coal-fired industrial revolution in the UK. We went to Coalbrookdale, the source of the industrial revolution, and then traveled in Iceland and around the UK looking at geothermal and other energy sources. And more recently, there's been this course that we run to New Zealand, first in 2013, and more recently as a one semester course in 17, 18, 19, and 20, although we're ready to go, actually did not happen. It's interesting. And so the premise of that class is sustainable energy in New Zealand. New Zealand happens just to be perfectly geologically set, perfect geological setting for geothermal energy, as we'll see a little later. But to talk in general about it first, Richard Smalley, who was a Nobel laureate, he received the Nobel Prize for C60, carbon 60, buckyball, so to speak. And his contention was that the energy, well, the issue of water supply is not a problem. As long as you have enough energy, you can always desalinate. Water supply on the planet, we've got a ton of water in the ocean. And if you want to get potable water, you could desalinate it. And the only problem then is energy. So he took energy as the single most important requirement to life by humans on this planet. And solving that is important. And of course, his prognostications about this were around the time of the climate awareness and the carbon problem awareness, but really didn't address it. And so if you can solve the carbon problem and get energy at low costs and easily available, then perhaps you can solve many of the other issues. Of course, if you're burning, if you're using biodiesel by substituting growing crops for fuel, for growing food, you necessarily have not solved the problem because you might have a shortfall in agriculture. The second quote, the bottom, is from John Holgren, who 2 administrations ago was Obama's science advisor, and basically saying that the environment, economics, energy nexus, where these all come together, having energy that's affordable and environmentally responsible, is a key problem to solve for life on the planet. So you're all aware of these things, right? You've gone through this. This is a visualization by a guy called Hans, again, you're covering up half my screen by your pictures. I'm going to take your pictures away. Is Hans Rosling. I was going to say Hans Rossman, but it's Hans Rosling, who's a Swede, who was a doctor who worked in Africa, a physician who worked in Africa, and ultimately returned to Sweden and was fascinated with the idea of presenting statistics to people. And so this, so for some reason, PowerPoint, I should never use PowerPoint. I think it wants me to be able to not use the things that are on the bottom of my screen, but to use my advance and backwards buttons. Yeah, it does. So rather than just use my arrow buttons on the keyboard. So this shows income per person, or income, I guess, per person, which is capita GDP divided by the population versus energy per person. So shown on this are the dots by size are the population, and by color are the continent from which the dots come from, and the labels are for countries. I labeled them actually based on the nationalities of people in the department that you are part of, energy and mineral engineering, not the program necessarily, but the department. And so I'm going to take it back to the start. The first vertical ordinate is energy use per person. And you see that this is a log-log scale, and it's basically a linear line with what would we say the most developed countries in the top right-hand corner and the less developed countries in the bottom left corner. And the second graph is the CO2 emissions per capita rather than energy use per capita, with the same basal scale of income per person. And so you'll see in terms of the evolution of this, it actually follows pretty much the same form as the previous graph. So-called wealthy and First Nation countries are shown in the top right. I guess it will stay there now, so I don't have to do anything. And developing countries further to the bottom left. But they are on this trajectory from bottom left to top right. And so the point is that both in terms of energy use per capita and in terms of carbon per capita, the aspiration to be a wealthy country where you can live well, live comfortably, live securely, not including gross domestic happiness as they talk about in Bhutan, but in terms of finance, purely in terms of economics, everyone aspires to have a high energy dense economy because that supports a high standard of living. And all the fact that these two graphs, both for CO2 and energy, are common to each other means that most economies are using high carbon environments to be able to generate that energy they use for their economic system, to boost their economy. And so that's the premise of that. So it's quite topical, I guess, from, it would have been 4 years ago now, the outgoing Obama administration. It's unusual, I think, a first maybe for an outgoing president to publish a paper in Science, a top scientific journal, but it basically was self-lauding the achievements in their administration in a reputable scientific forum. And paraphrasing what that paper summarized, the observations were that greenhouse gases had dropped on 4 different occasions. in the 80s, early 80s, 1992 and 2009. All of those were associated with major contractions in the economy, a bad thing if you're thinking in terms of jobs and income. But the one that occurred in 2014 was a time of record growth, or at least growth. And so the possibility was that having high energy intense economies might not necessarily fully be linked to carbon in every eventuality. And so the 2014 growth possibly was due to the use of lower carbon fossil fuels, as in natural gas, replacing coal and doing it naturally, and not necessarily an outcome from the administration, but nevertheless it pointed to a path forward. The other observation was that electricity generation had changed. Instead of being predominantly coal, natural gas available through shale gas, not universally lauded as a desirable source, had taken over naturally, not by any government incentives, but just as being cheaper than coal. Employment in the renewable energy area had increased and was much larger than the fossil fuel industry. And that indeed the whole premise of having to have an energy intensive society, to have a rich and society in which people lived well, was not necessarily proven, as energy use had actually gone down through the administration, but the economy was still strong. And so those are the premises coming out from that administration. The US, along with most other industrialized nations, is mainly a fossil fueled economy. You might have seen before these Sankey diagrams, so-called Sankey diagrams. This is more recent than 2009, which it says at the bottom. This is probably a more recent one, probably a couple of years old. And it shows the flow of energy through an economy from recovery on the left-hand side through to utilization on the right-hand side. And you can see that the different sources for the US, roughly 70%, I guess, would be fossil fuels. So petroleum, biomass, coal, well, biomass isn't fossil fuel, but coal and natural gas are. The numbers below those boxes refer to quadrillion BTUs. And so the US uses 100 quadrillion BTU per year, which is the same as 100 exajoules, which is about the same as 100 trillion cubic feet of natural gas equivalent. That's a good number to remember. The US uses about 20% of the world's energy. So the total consumption worldwide is about 500 of each of those items. And so the US uses about 20% of the world's energy, but has about 5% of the population. So 300 million out of 6 billion, right? That's order of magnitude, maybe 7 billion, but that order. And so you can look at those statistics and decide whether they're ethical and appropriate themselves. But regardless of that, the numbers on the left-hand side should total to about 100 quads. And then you see about 70 quads of those are fossil fuels, and a much smaller part are the renewables as the top 5, geothermal being 0.224 of a quad. So I guess that would be 0.224% of the energy usage in the US. And so this was the roadmap that was thought to be the Obama administration, now dated, of course, 2009, been the inauguration. The logical way of looking at the way forward. And so the way forward was one of being able to deal with this by swapping out fossil fuels for renewables, dealing with fossil fuels by perhaps storing the carbon from the burning of fossil fuels in the subsurface, so it's not in the atmosphere, looking at methods of energy storage, which is important, I guess, for intermittent resources like wind and solar, and improving the grid so that you could actually deal with renewables. And I guess the other striking thing about this is in terms of end use. If you look at the use of these, something like, is it 50% or 59.1% of the energy is rejected energy. It's wasted. And so utilizing that for district heating or district cooling is an important change that can be done. Even without changing anything, you can get more energy out of the grid if you better use the material. And so looking at that Sankey diagram informs methods of being able to reduce the use of fossil fuels and boost the use of renewables. And so the desire to do that is built on this idea of global climate change and human-induced climate change. And that all relates to the fact that if you look at the sources and sinks of carbon on the Earth, there's a lot of carbon. Most of it's immobile. When it sits in carbonate rocks, limestones, and when it sits in coal, it's not active within the atmosphere. But as soon as you utilize it, as my colleague Jonathan Matthews would call oil liquid sunshine, because it's fossilized biota, right, over time, that's sequestered in the ground and only comes out when we utilize it much faster than nature would otherwise have done it. There's these very big carbon reservoirs. So these numbers in these boxes are sizes of the reservoirs in terms of pica-grams of carbon. I think they're billions of tons, but I'm not sure what the conversion is. It doesn't matter. So the numbers in the boxes are the reservoirs of carbon. The black numbers are the natural reservoirs. The black arrows are the natural fluxes of carbon between different reservoirs, say between the surface ocean and the atmosphere, which is 70.6, I think it's a billion tons. Yeah, it is, actually they are billions of tons, because the 5.4 is the one out of balance one, which is what humankind have put in by burning fossil fuels. So 5.4 billion tons, gigatons per year of carbon, not CO2, but carbon. So if you multiply that by about 3, you end up with the amount of carbon that's put out per year. It's an old figure, but it makes the point. And so that's a relatively small flux compared to those other natural fluxes, 70.6 and 70 being the exchange between the ocean and the atmosphere. But that unnatural flux put in place by humans is enough to result in this buildup of 161 billion tons of carbon that's sitting in the atmosphere and is the change that is being wrought by humans. And so this is well documented in the left-hand side figure, which shows the changes in concentration of carbon dioxide in the atmosphere and of methane and nitrous oxide as well over time. The so-called hockey stick diagram with these big increases in concentrations in recent post-industrial concentrations. And I guess all I'm trying to make the comment for in this slide is that it's necessary to turn that change in concentrations. The concentrations aren't problematic for us in themselves. It's the ramifications for those concentrations are in terms of the greenhouse effect, in terms of how much solar radiation is able to escape back into space after it's shone on the planet, and how quickly that buildup in temperature, the change in temperature that we have seen and expect to see on the planet, which we can calculate reasonably straightforwardly, actually, what it would be if we know what the changes in concentrations would be. So the changes in concentrations are quite well known. They're quite as predicted from the amount of fossil fuel we burn. The predictions of what they will be are quite easily predicted. Their impact in terms of changes in temperatures are quite easily predictable as well, except there's some unknown sinks for temperature on the planet that we don't know. But I guess what is the debate that exists across the political divide is what the impacts are of those changes in concentrations and temperatures if they evolve. Are they catastrophic to humanity, or are they inconsequential? And so that's really the debate that's continuing. And I really like this slide. You'll see it as it evolves, but making the case. And that the case is that the science we've known about for some reasonable amount of time. We quite well understand the science. The science hasn't changed from 2000, which was George Bush's inauguration in 2001 to now. But the interpretation, political interpretation of what should be done really has changed. And so all the things that we deal with should be, I think, right? Scientists shouldn't be running the planet. Elected officials in a democracy should be making the decisions as to what is done with the information that is supplied by scientists. And so kind of that's the environment that we work in. So this is dated, but it's an appropriate illustration of what can be done. It was the Obama administration's plan for climate change in 2009. Pat Deemer was the head of the DOE Office of Science, the secretary of the Office of Energy. So Department of Energy, the secretary was Stephen Chu, a Nobel laureate, which was the first, I think, to have as a secretary. Pat Deemer was running the Office of Science within DOE, and that was the body that was looking at the potential outcomes to the climate issue. And so here's our 4 potential outcomes. And so conservation, you drive smaller cars, use less energy. We talked about the fugitive emissions from energy consumption on the right-hand side of the Sankey chart. You use electric cars because you can charge them from static energy sources, either powered by coal with the CO2 being pumped underground or by natural gas with the CO2 going underground. You can boost renewables slowly but inexorably. And you can do this by implementing a cap and trade system to be able to accommodate it. The cap and trade system, I think, was tried in June of 2009. It failed in the Senate and was never revisited. It failed absolutely. And so it wasn't put in place, but in terms of a viable energy plan, those are the kinds of things that could be done. And I mention that because it makes sense in terms of what we might be talking about in this class in terms of viable solutions to this. Geothermal energy, of course, is one potential one, but there are much broader array of subsurface solutions to that, such as pumping, utilizing natural gas and pumping the CO2 from it underground, which of course, you could actually use that. People have talked about using that as the heat transfer fluid that gets pumped through a geothermal reservoir instead of water to be able to recover the heat from it. And so there's lots of nuances in terms of energy recovery. This is an important graph that you might have seen before. The original paper is in Science by Pakala and Sokolow, both at Princeton, I think. They're still at Princeton. And it looks at the carbon production per year on the left-hand axis with the number of years. It was published in 2004, hence the start and the branch in the road symbol there being that you have an option starting then. In 2004, the annual production of carbon, not of CO2, but carbon of the world was something like 7 gigatons, billion tons per year. And the trajectory was that the amount had been increasing and was presumably going to increase. And so to deal with the carbon problem, what you could do is you could stop all carbon increases in carbon production from occurring, and you could try and go on a trajectory that would accommodate that. Alternatively, you could take 50 years to try and reduce the amount of increase in carbon production, stopping it in 2050, which is what people are talking about now, of course, the 0 increases in carbon. Actually, people are talking about carbon neutral, no carbon output in neutral. So 0 carbon output would be 0 carbon on this. It means that you're not emitting any carbon into the atmosphere. And so this paper from now 17 years ago, was making the case that this stabilization triangle, you could think of as being a number of stabilization wedges. Each of these wedges would be reducing by 1 gigaton of carbon per year, the increase of carbon over 50 years. So each of these wedges would be 1 gigaton by 50 years. So 25 gigatons of carbon that you're removing from emitting into the atmosphere. And to do that, we can get this whole stabilization triangle if we can look at 7 of them. But what the paper was making the point for is that people have a hard time visualizing what 25 gigatons of carbon making up one of these wedges is that we can avoid. And so you have to put it in some terms that people can understand. And so each one of these stabilization wedges, you could get there by any of a number of different ways. There happen to be 7 on here, and there's 7 wedges, but that's not really the point. Each one of these wedges you could get by doing a variety of things. And so the 4 things that are relevant to this class, partially relevant because they deal with the subsurface, would be that you introduce baseload geothermal, and you replace 800 gigawatts of coal-fired generation, 800 power plants in 50 years that are burning coal right now, and you replace that with the same amount of energy coming from geothermal energy. It's a big ask, of course. You could pump the CO2 from 800 plants underground and keep it sequestered, still burning coal, business as usual, or burning natural gas, business as usual. You could use nuclear power by putting 800 new or 700 new power plants online, which is perhaps not many environmentalists' view of a good substitution in terms of energy. You could get wind and solar online and take care of it by replacing another 800 power plants by wind and solar, which is getting more viable these days. You could increase the reduction in consumption by putting electric and small cars on the road. Or you could switch fuels, and instead of burning coal, you could burn natural gas. And if you do that, then if you replace 1,600 power plants in 50 years with gas-fired power plants, then you also have the same outcome. The double number is because you still emit carbon from burning natural gas, but natural gas is about half the carbon output from coal. And so those talk about the kinds of things you have to do to be able to take care of one single one of these wedges. And so in terms of subsurface resources, there are a variety of different options. Low carbon solutions are burning gas, and gas can come from shales, from coal by taking the gas only out of the ground, and from methane hydrates. Carbon management solutions involve pumping the flue gases underground and having business as usual. And zero carbon solutions that we'll talk about here. We're going to talk about geothermal in general, and EGS is one of the ones that we talked about, I guess, 2 days ago. Nuclear power is one. Hydropower and using pump storage is an alternative. And of course, the ones we won't talk about are wind and solar. You can talk to Susan Stewart and Jeffrey Brownson, Frey Brownson for those. So let's go through each of those in sequence, just relatively quickly. I guess I've had to get oriented for this class. So I guess we have until 20 after, right? 20 after 1. We've got plenty of time. I'll go through this moderately quickly, just to give an appreciation. Well, for the last 15 years, the whole economy of Pennsylvania, for one state, has benefited from the so-called Shale Gas Revolution. The Marcellus is what sits under our feet, together with the Utica Shale. Those shales are present all over, broadly distributed across the country, in Texas, in Michigan, in Oklahoma, also in Western Canada. They're pretty widely spread, and they represent a very big reserve. Something like the Marcellus is supposed to be about of the order of 1,000 trillion cubic feet. And so if we're talking about running the US on 100 trillion cubic feet gas equivalent for 1 year, then you could run the US for 10 years just based on what's present in the Marcellus, if you can recover it, if that reserve is fully recoverable. It's not. The big innovations that occurred that allowed these tight gas shales to be recovered were 2, and they were horizontal drilling. where you drill down to 3 kilometers and then vertically, and then you have your hole run a couple of kilometers horizontally within the shale horizon. And the second innovation was massive hydraulic fracturing, to be able to break up the rock, to be able to give it lots of surface area. Actually, something that's not dissimilar for geothermal, EGS geothermal, you have to create heat transfer surface area. But these shales were all of a sudden viable in terms of recovery of gas, only with these two things: horizontal drilling and massive hydraulic fracturing. The cameo at the bottom, by the way, is the gas fields off the southwest coast of New Zealand, by the way, because this was a presentation originally developed for the New Zealand Rotary International, I guess. So natural gas comes from gas shales. It's been a very convenient one for Pennsylvania and has been a great boy, I think, to the economy of Pennsylvania for the past decade and a half. Less so now, I think, as oil prices are lower. You can also get natural gas from coal beds, not extracting the coal for burning as you would do in shoveling it into a power plant, but merely drilling wells into the coal seam and recovering it just like you would in gas shale. The reserves are much less, perhaps a tenth of the amount that's locked up in gas shales. 100 trillion cubic feet recoverable up there on the top left-hand side is identified. But the mechanics of pulling out the natural gas is much the same as doing it in coal beds. And the third big new source, of course, the source of natural gas that's been used has been just conventional reservoirs. So much of the natural gas that has been used in the past has come from the Gulf of Mexico, from natural porous reservoirs, not these unconventional gas shale reservoirs. And that's still available, but is dwarfed by the potential reserves that are present in the gas shales. The other reserve, which is available, which is not tapped, which is a massive reserve, is as hydrates. And so offshore and also in permafrost, natural gas exists. It's locked in kind of a cage of ice. So it's within ice, it's frozen within ice at a molecular scale. And by thawing it out, either by heating it, by dropping the pressure, or by adding enablers, such as salts, right? Same as you melt ice on the roadway, you can actually unlock it. And it's a double-edged sword. Double-edged sword is that the reserve is huge. You see on the bottom of the figure, it's something of the order of between 100,000 and a million trillion cubic feet of gas. And so if you need 500 trillion cubic feet of gas to run the world for a year, you're talking about a 10 to the 6, you're talking about 2,000 years of supply to run the world. Of course, it's not carbon free. And the issue is that it's really difficult to recover. It sits offshore, it's not concentrated very well. And the very recovery of it jeopardizes the stability of the deposits in which it's stored. And you can result in massive releases. But it is a large reserve. And so for any of those, using natural gas, you can look at replacing power by 1,600 large coal-fired generating plants with natural gas burning power plants. And that would give you one of those small slithering wedges, of which we need 7 of them to account for the whole stabilization triangle, and to do that over 50 years. So natural gas is one source. The important thing about natural gas is that the reduction in greenhouse gases that occurred in 2014 that was noted in the Obama paper was probably as a result of the fact that natural gas all of a sudden was cheaper to burn, cheaper to recover and burn from gas shales than coal was. And it has basically displaced coal and reduces the emissions as a result. So that was an economics-driven resolution that happened naturally without any kind of government intervention. And that's something that's been elusive in terms of the many years of climate talks that have been occurring since Montreal and Kyoto, and coming up to Paris in 4 years ago, I guess it was, and coming up to Glasgow, which would have been this past year, but now is postponed until next year. And so it's been a difficult problem to solve. So natural gas has been a natural problem solver, but clearly isn't a complete solution. A secondary solution in terms of carbon management is to burn fossil fuels as normal, coal and natural gas, but take the off-gassing components and sequester them, resequester them underground, either in coal fields, either in existing reservoirs, depleted petroleum reservoirs, or in saline, non-potable waters in the subsurface. I guess these are hydrocarbon reservoirs. These are saline reservoirs. So in other words, reservoirs that contain brine, that are used for injection of fluids already. In the US, there's a disposal program where noxious fluids are disposed of underground. For instance, fracking water isn't disposed of in Pennsylvania underground. It's disposed of next door in Ohio, where that is permitted, not permitted in Pennsylvania. And to have the very large volumes of flue gases emitted from fossil fuels stored with no emission to the atmosphere. Of course, that's a big ask. It's a big ask because basically the amount of fluids that you have to sequester in the subsurface have to be of the same scale of the fluids that you're burning in terms of oil and coal in the planet. And so it's an industry that has to be built, that has to sequester these things, that's not making money because you're not making money selling electricity, you're actually costing you money to do it. And so, but nevertheless, it's a solution. And to be able to do that for one wedge, you have to convert 800 big power plants burning coal and take the flue gases from them and sequester all that effluent in the subsurface, which again is a big ask. In terms of zero carbon solutions, ones that don't really have much carbon attached to them, some carbon perhaps, but not much, certainly not on a scale of conventional fossil fuels, geothermal is one of them. We'll talk in more detail about the methods of geothermal recovery, but I would say that the holy grail of geothermal energy recovery is what's called EGS solution, enhanced or engineered geothermal systems. And the idea is that you go under New York City, for example, you drill a hole that goes down to 5 kilometers where you know it's going to be hot. You drill this blue borehole that might cost you $5 million or $10 million to get down there. You create a reservoir that's not existing, that has permeability by kind of hydraulically fracturing it. And then you circulate cold fluid from the blue well into a return well, which is the red well. And you bring it up to the surface and you use that to generate electricity. And you can do that anywhere in the US if you can solve the problems of being able to develop the technology to do that. Existing hydrothermal plants do that already, but they exist only in places where the crust is allowing you to do that. And those locations in the US would be on the West Coast, California, the geysers north of San Francisco, and in Oregon and Washington, where there's some other geothermal, where there's a plate boundary. And the rest of the crust in the US is old and kind of cold, warm enough to be able to go down 5 kilometers. We talked on Tuesday that geothermal gradients are something like 25 to 50 degrees centigrade per kilometer. So you can get to 200 degrees centigrade. And so long as you can get above boiling, then you can generate electrical power by flashing hot water to steam and then using that to be able to generate power. And so if you look on the top right of this, EGS, if you look at the reserves both of hydrothermal, which would be the geysers, the reserves are something like 10 to the 4 exajoules. And so the US runs on something like 10 to the 2 exajoules per year. So I guess there's 100 years worth of hydrothermal reserves available in the US to run for 100 years. But the EGS reserves are huge. The question is whether you can actually tap them or not. And so you can do the calculation. Crath rates were something like 10 to the 6 exajoules at the upper end. So the geothermal resources are 10 to the 7, so 10 times larger than the amount of natural gas that's available. So the reserve is really quite large. And in terms of background, the methods of recovering geothermal heat vary on this spectrum that's shown on this bottom part. The spectrum is from normal hydrothermal reserves sitting on the flanks of volcanoes and plate boundaries, like the geysers in California, where you have a reservoir at depth which has fluid in it and is already broken up by the fact that it sits on the plate boundary. And so you can circulate water through it quite quickly and recover the heat. And at the other end of the spectrum, we have these so-called engineered reservoirs where you have to make it. You have to drill down. There's no transmission in the crust. It's warm, but you have to develop a heat transfer radiator, if you like, to be able to recover the heat from the subsurface and use it on the surface. And so those are the spectrum of reservoirs that we'll talk about in this class. And I guess also in addition to that, we'll talk about in 10 to 50 meters below the surface, we'll talk about ground sourced heat pumps and also aquifer thermal storage as much shallower subsurface solutions to this. And the challenges for this are that if you drill a well in New York City and you spend $10 million to get it down to 5 kilometers, then you have to be able to pay that well off over 30 years of the plant. And to do that, you have to get enough energy out of it to be able to make it worthwhile. And so the minimum production that you need is something like the order of 100 kilograms per second of water per well at, say, 200 degrees centigrade to be able to get enough energy out of it to pay for it. And so if you can't do that, then you don't have a viable well. And if you look at the demonstration projects that have been attempting to do enhanced geothermal recovery over the last, well, the first one at Fenton Hill was in the 70s, Los Alamos. So I guess that's 50 years before now, is if you look at the production from them, only in some cases has that criterion be met. And so even though the resource is very large, whether you can turn it into a recoverable, useful reserve or not is still an object of investigation. And so for geothermal, just as in the others, you need to be able to replace 800 coal plants, coal burning plants with geothermal. And the equivalent in terms of the gas usage is something of the order of 40 trillion cubic feet per year. So zero carbon solutions. Geothermal is clearly one of them. Nuclear really is one of them. Not so palatable to some. Not so palatable because there are some risks. And with risks, there's a risk of Fukushima or Chernobyl or 3 Mile Island. Those are largely circumvented because you can develop reactors that only supply fuel at a sufficiently low rate that a meltdown is not so likely. But the other inherent risks are that you have to take care of the products of the reaction. You have to dispose of the wastes. And also this issue of nuclear proliferation is that as you reprocess the wastes to be smaller wastes, but more toxic wastes, then those are closer to being bomb grade materials, nuclear weapon grade materials. And so there's this trade-off between having lots of low grade waste, which isn't useful in a proliferation or isn't a hazard in the proliferation sense, to having highly reprocessed waste, which is highly usable as fissile material for nuclear weapons. And so the subsurface part of this, which is kind of related to this class, I would say, is the disposal of the radioactive waste. We have to do this anyway because they're sitting on site. The 1985 Nuclear Disposal Act has still not been honored. It was supposed to put in the ground beginning in 2000 nuclear waste. Still hasn't happened in the US. It's happened elsewhere in the world. The former potential repository for the US was at Yucca Mountain, 100 kilometers northwest of Las Vegas, on the Nevada test site, a kind of prohibited area that had been blowing up nuclear weapons until the 1970s and late 1970s when they stopped. And the picture in the top right is the so-called drift scale test, which is a test that was run on this test site starting in 1998, I think, December of 1997, I think it was started, heating up a drift for 4 years, cooling it down for 4 years, and looking at the behavior to be able to understand whether you could actually store the radioactive wastes in place. So this is kind of the layout of the so-called Yucca Mountain as it would have been. And it's a tunnel that goes down to depth. It's about 300 meters deep. Amir, why didn't you come back? And that 300 meters depth, then you drill a whole bunch of tunnels. And into these tunnels, you drive railroad cars that contain the spent fuel. You leave it there for 50 years and ventilate it to cool it down. After 50 years, you backfill it with something, probably clay, that has low permeability and also works as a good sorbing agent for radionuclides. And then you put a plaque on the surface and you abandon it. And so Yucca Mountain was the prospective site that was seeking licensing for the disposal of the US civilian waste. In January of 2009, as part of the incoming Obama administration, a blue ribbon panel was put together to evaluate whether that should be the site. And it was a contentious issue because the healthcare bill that was needed at the time, with the powerful senator from Nevada, Harry Reid, was not excited about having nuclear wastes repository established in his state. And it was thought that this was some kind of peace offering to get healthcare dealt with. So it was a political issue. So in 2000 and, I'm not sure where this is going. So in 2009, it was put on hold by the results of this blue ribbon panel. It was subsequently put back in action as a potential site by the courts under the observation that the president couldn't act against an act of Congress. And it's still kind of in limbo right now with no definitive, no work at Yucca Mountain, but no definitive proposal for the permanent disposal of civilian nuclear wastes, etc. That's what these other slides are. And in fact, since nuclear disposal at Yucca Mountain was taken off the table, there was some investigation of other solutions. And those other solutions got to potentially drilling a very wide diameter hole, maybe 1 meter in diameter in the Dakotas of the US, down to say 5 kilometers, in which material would be placed and dropped down and then sealed back in, much in the same way as at Yucca Mountain. Yucca Mountain was 300 meters below the surface. This is talking about 5 kilometers below the surface. But the same kind of idea, putting it away from humanity, where the components can't come back to haunt you through the groundwater system. So that's it. So in terms of subsurface solutions, geothermal is one of them, which we'll talk about in this class. Nuclear power could be a viable solution. Hydropower is one that we won't talk about, and the normal solutions being wind and solar in terms of renewables. I threw this slide in. Our course that we ran to New Zealand in 2013 was called the New Energy Deal Down Under, for Down Under being a location, looking at New Zealand in terms of its energy portfolio, if you like, and trying to contrast an industrialized developed country like the US that has a particular energy portfolio with New Zealand, which is largely a rural and agricultural economy with a strongly developed renewables-based energy economy through geothermal, and comparing it also with Australia, which is a developed economy, less agriculturally based, but strongly mineral based in terms of coal natural gas, and also minerals. And so we predated the Green New Deal, but the Green New Deal is essentially, as you know, the idea of having more renewables put into the energy portfolio, and the exclusion or reduction and ultimate exclusion of it, as it has to be, right, in reality, of fossil fuels. Whole question, I think, is for society is, what's the time frame of what that occurs? Is it over 2 years, 5 years, 10 years, 30 years, up to 2050 and beyond? And so that's something that's part of our deal. And so I won't talk about this. This is a different presentation, only to make the point that we do run this class. If you're still around in 2022, join us, and you perhaps will have hoped to have graduated by then. But New Zealand has a similar Sankey diagram to the US. It's a much smaller energy economy, roughly scaled with its population. Its population, I think, is of the order of 300,000, and it's 3 million instead of 300 million, as in the US. And the energy consumption, instead of being 100 exajoules, is of the order of 1 exajoule per year. But in terms of makeup, it actually still uses a lot of fossil fuels, although the one thing for New Zealand is that it exists on a plate boundary. I don't know if there's a picture here. The plate boundary on this map is off to the eastern side of the North Island, so you don't see it here. But it sits on a plate boundary, so it's ideally located for geothermal energy. But of course, right now, geothermal energy isn't a useful form of energy to be able to run internal combustion cars with. And so you still need transportation fuels, and you still need transportation fuels to run airplanes for the moment. Cars are much easier to run as electric cars. Airplanes are much less. And so I won't go through the rest. But the point of today's discussion, well, not much of a discussion, it's kind of been one way, hasn't it? I hope you're still with me and still awake, has been to make the case that this class is looking at one subset of a form of subsurface energy solutions, and that's geothermal energy. There are a variety of other important uses of the subsurface, both for recovering energy, petroleum, natural gas, coal, which we won't talk about, but are there, part of the background. The important perspective, I think, for natural gas is that it's a replacement, a bridging fuel with lower carbon that has displaced a high carbon fuel naturally through its own positive economics, and has succeeded in doing something that many decades of climate discussions and conventions have failed in doing. And so it's to be lauded for that, but clearly it is a transition fuel to a zero carbon future. And in terms of that zero carbon future, potentials include both nuclear power, the disposal aspects, which we're not talking about in this class, but which is one of the options. Disposal of the production wastes of CO2 from business as usual, which is also a viable solution to the carbon problem in terms of going on burning fossil fuels as we do, but not suffering the negative impacts because you don't put the carbon into the atmosphere, you sequester it somehow. The problems with that are that, one, you want to be assured that it's going to be secure in the place that you're storing it for many decades or centuries, and that you can sustain the costs of doing that. It's not inexpensive to recompress the flue gases and to supply them to the subsurface so that they are present in the subsurface. And so of the other two viable ones, nuclear power, the connection with the subsurface is that you have to dispose of the waste. I guess you have to mine the uranium, but you have to dispose of the waste. So innately you're using the subsurface in that, but that's not really part of what we'll talk about. And in terms of geothermal energy, actually a lot of the technology which is used for the recovery of geothermal energy is an adoption, if you like, of the technology that's been developed over 100 years for the oil and gas industry. And the new revolution in terms of the shale gas revolution, in terms of drilling horizontal wells and stimulating the reservoir to bring its permeability up from zero permeability essentially to some manageable permeability to recover the gas, is really not very different from the technology that you have to apply in the subsurface to be able to develop enhanced geothermal systems to be able to create heat surface area in the subsurface and to have a heat transfer fluid that you circulate through it effectively without using up all your power pumping it, and being able to recover heat easily enough and at high enough temperature to be able to use it in some reasonable way to either generate electricity or to use it as direct use by heating, by district heating uses. And so those are kind of the big pictures of where we are. And so like anything, all of its choices, you as engineers and scientists should understand in detail. Certainly some of our policymakers don't understand some of this or don't want to understand some of this. But it's your job, I think, to understand the mechanics and physics of how this works and to reason as to what we would use, and to be able to inform policymakers as to what should be used and how it could be used to be able to satisfy our life and existence on the planet as we push ahead into the next decade. And so I'll leave it at that. I'm not sure I've closed it particularly well, but that's the big picture. So as of Tuesday next week, we'll start talking about the mechanism by which we get 50 degrees or 25 degrees centigrade gradients of heat down from the surface of the Earth, why the Earth produces that, and we'll deal with it from then on. I guess some people joined us late, so I will make the point that I made in the early minutes. One, you got email today, you should log on using your Penn State credentials. Otherwise, I won't credit you with being online for however minutes Canvas or Zoom tells me that you've been online. I can't check that you're active in that time, and I don't need to, but I will check on time spent, if you like, in Zoom. So do that. And also, if you want to get this presentation and also the stuff that we'll use in the future classes, look on Canvas under Files, and you should find it there. If you did log online today and you're on your PSU credentials and you're logged on not on your PSU credentials on Tuesday, then I will convert your score to reflect that. And other than that, after talking using PowerPoint, which I don't think we'll revisit in this class, for an hour and 2 minutes by my clock that's here, I will stop. Any questions? I've lost your faces. I guess I'm still online. I don't even know if I am. Yeah, I'm sharing my screen still. If I look at everybody.
On the first slide, or maybe not the first slide, but the one with like the US Sankey chart.
Yep. You can go there, yeah.
That large portion of like 59.1, like unused. What, like, why is that unused?
It's waste heat. So when you generate thermal heat with a coal-fired or any nuclear power plant, usually you put the hot water into a river that heats the river. And usually there's constraints on the fact that you can't do that because you'll deoxygenate the river. And so it's just rejected either as heat going out in water or actually heat going out mainly in steam. So at most power plants, when you see these big plumes of white smoke, it's not smoke. It's a mixture of carbon dioxide as flue gases, but the vast majority of it will be just water vapor. And so it's going out as water vapor. And so if you can harness that to be able to use it to be able to heat a district by pumping it around someone's radiators in their apartments, then you can harvest that. And I guess also on Tuesday, we talked about the fact that Cornell has a plan. They have a big grant from DOE. Well, I think they have $7 million to drill an exploratory well. I'll let someone in. Someone's joining now. I don't know if they dropped out or not rejoining, but Cornell plans to do exactly that. They're going to drill a deep well, and they want to use that. The crust isn't warm enough in Ithaca, New York, not very far from here, to be able to probably get boiling water out of the ground. But it is warm enough if you can get water warm enough to warm up people's apartments. And of course, you probably realize that you don't actually have to get above 100 degrees centigrade to generate power from water. You don't need to necessarily flash the water to steam. What you can do is you can transfer the hot water into a binary agent such as IPA, isopropyl alcohol, which has a boiling point of 38 centigrade. You can flash the alcohol to steam. You can use that in a closed system, closed loop system, to run a turbine, and you can recondense it, and then you can use it. So, but making electricity from hot water is not as efficient as using hot water just to heat straight without, you can heat your house with an electrical baseboard, so you can boil water, create steam, create electricity, and use that electricity to heat your house in an electric baseboard heater, or you could heat your house directly by using the hot water from the plant, cutting out all the inefficiencies of those parts. And so it's, you could use that. It's a long answer for your very simple question, straightforward question, but it's coming out the stacks as vapor, water, and condensing. You'll see these cooling towers, these parabolic cooling towers, are attempting to condense some of that vapor so you can actually reuse the water, both in the boilers and also reject some of the water to surface water into rivers. Okay. Good.
And New Zealand's was much smaller than ours.
Good question. I think the right-hand side components were different parameters that they defined. I can't remember.
Okay.
And I haven't looked at it in detail lately. So yeah, they weren't looking at rejected. They're looking at the uses, and they didn't ultimately divide them into rejected into those two categories. The two categories on the right-hand side of the US one were useful energy and rejected energy. And these are just the end users of this. So whether it's commercial, residential, industrial, etc. uses. So just a different right-hand side.
Okay.
Good chart though. It says a lot about life. And I think it's probably, certainly the US will be having a higher proportion go to renewables, and certainly a reducing amount for coal, mainly taken up by an increasing amount with natural gas. I think. Good. Any other questions? All right. All right. Well, we're done a few minutes early, I guess. Yeah, we're 8 minutes early. Doesn't matter. We don't have to use up a full 75 minutes. So on Tuesday, if there are PDF files of what I'll use in class, I'll try and upload those to the share place on Canvas. That's the easiest place to, actually the easiest place to put it ultimately will be on my website. But so for now, look in Canvas if you want to get those. Join early if you wish. Please join on time, because I don't like, someone's joining. Jared Llewellyn, are you coming in now because you've only just joined, or have you been dropped off? People might get dropped off their connections. And so I don't have anything more to say. So I'll look forward to seeing you on Tuesday. Enjoy your weekend. No deliverables. Think about the class. And I guess I'll be working hard on putting something together for Tuesday, right?
Have a good weekend, Professor.
Thank you. Have
You
a good
too.
weekend.
Thank you.
Thank you. Take care.
Thank you.
Yep. Bye-bye.
Bye-bye.